So, thank you very much for the introduction. I will present today my work I did together with Rainer Knapke and Helge Patz-Jägler. You probably know the problem that you always have to do some profiling, some tracing to find bottlenecks to improve your software and everything. And if you are working in user space, that's pretty fine because there are a lot of tools that help you with. And what the normal thing is that helps you with is the operating system. But then the question arises, well, when you're writing system software and writing the operating system, how do you trace and profile that? Because in the end of the day, it's still a piece of software that has especially work very well and very fast. It turns out that the common approach today is in-system profiling with, for example, perf. Where the tracing itself is integrated in the operating system and the tracing statistics are gathered by the operating system itself. Unfortunately, this approach has some drawbacks. That is especially the case that it introduces some bias which comes through the tracing overhead and the data collection and storage itself. As you can imagine, if you trace the operating system and trace a scheduler, for example, the scheduler subsystem or another subsystem that is called very, very frequently, you will generate a lot of tracing data and you have very, very short functions that are executed. Furthermore, the drawback is that your results may be not so easy repeatable, especially if you write system software. Sometimes you need some deterministic evaluation because, for example, the order in which your task executes, the order in which your interrupts are handled might be critical, and to repeat the experiment might be crucial to find a very specific bottleneck. And in the end, with in-system tracing as today, not everything is traceable in general. It can be two reasons. For the one, if you have a piece of software, if you have a piece of bare metal software, for example, there is no in-tracing, system tracing, because you haven't implemented it, or you have an operating system like Linux that has built-in tracing facilities, but there are still several functions, again, like the scheduler, that are not traceable because they are often called too frequently, or they are part of the tracing itself. So we thought about that issue and came up that it's maybe a better idea to look from the outside of everything and not do the tracing from the inside of the system we are interested to observe. And we didn't want to start from scratch. As always, we tried to use as much as there is. So we started with the simulation part, looking from the outside. So we used a very established tool in the research community. It's the Jam5 simulator. For each of one who doesn't know, it's a tool that is used to simulate systems, to see very details of the CPU, where you can model the CPU behavior, where you can model cache behavior. It's basically a tool to create a model of a system and then run software in it. A nice thing about this is that with the Jam5 simulator, we can execute, for example, the Linux kernel, also a piece of bare metal software, and it can extract the function calls with the help of the debug table. So how it works, it will look at the program counter and refer to function where it is in the end. So what you can see on this slide, you basically get out of the box with the Jam5 and you will end up with such a trace, which is very nice but not very helpful if you are doing tracing and profiling, because you cannot really see what the problem is. So we went on from this data and process the data further, and one result you can see here, which is for some reason rotated. I don't know what happened, sorry. Hopefully, oh, it gets worse. Sorry, it used to be the other way around. I'm very sorry. So you have here to look now from the left to the right. It's somehow color-coded on the intensity that your code is executed. And as you can see here now in this very brief example, it's just a cropped example because the one in total was too big. You can see one critical code path here. So you can already see which functions are critical to the system and might be worth improving, might be worth looking into do further improvements. Looking a little bit closer, again, sorry, it's rotated. You see what we are currently gathering for information. So you first can see how often a function is called during the evaluation, during the tracing you did, and how much time is spent in absolute in this function and how much time is spent in average. And also you can see, we'll get some information about the branches, so the sub-function codes, so you can see whether it's good to optimize the whole subgraph or just specific functions. So how good is this? Here you see some results we've gathered using our approach on the right side, and on comparison on the left side, the current approach within system tracing. There are two things you can take of the picture. So first, what do you see? This is a function trace of the Linux scheduler, so it's called very, very frequently, dozens and hundreds of times per second. And of course, it's very, very short because it's in the scheduler. And we did some experiment where we wanted to see how the run queue contention, so on the left is very high run queue contention, on the right side is very low run queue contention, behaves depending how much we change the execution time for each function call. So we artificially increased the execution time of this function that was traced here, doubling it every time. What we can now take from this picture is two things. First of all, if you look at the absolute numbers on the scale, you already see that the execution time through the in-system tracing program increased tremendously. So the tracing now takes up more than twice the time the actual normal execution of the function takes. So this introduces a lot of bias. And the second thing you see is that because of this bias, you cannot see the point anymore. So normally we would expect by doubling the execution time of this function to have equal distance between every graph. And as you can see, you cannot really defer this from this picture. So in the end, we have a much, much higher precision and a much, much better view on the true nature of our problem and the true execution times and the true results. So to conclude, because I have only a very limited amount of time, because it's only a short paper and introductory work, our simulation-based tracing and profiling approach has several advantages. As you have seen, we have little to none measurement bias. We have deterministic execution. In fact, we even stumbled about this problem because sometimes we want to differ things to see how it happens, and in our initial experiments, running every experiment again, because it's a simulation, again, exactly to the clock cycle, the same exact results. So you get like hundreds of thousands of function calls and you have exactly the same execution set. So it's very, very deterministic and very good to reproduce some issues. And the other big benefit is you do not need in-code tracing facilities. That means as long as your piece of software runs on the simulator we used, or another simulator, of course you can approach to another simulator, you can run a bare metal application, so you do not have to do extra work to do your tracing and profiling, and you already get your results. So as I said, we are just starting this work, because out of the necessity that we wanted to do tracing profiling in the scheduler. And what we want to do in the future is to introduce further performance metrics, because as you can imagine with a full system simulator, you can easily get values like cache misses, cache access, how everything you normally expect from a CPU you can extract and put into your results. We want to improve our data processing, because right now the post-processing of the information I showed you in the beginning is very hard, because we have to reproduce the whole call stack, because as you can see, there's no relation between the function calls. We only see which function is called and not which function involve which other sub-function. And ultimately, if we succeed in our work, we want to build an easy framework that makes it very, very easy to put in just your software you want to evaluate and get the results just through clicking on a button, having the graphs generated very easy for you, and not as it is today, just as a command line application. So thank you very much for your attention, and I'm happy to answer questions.
Any questions?
Yes?
How easy is to correlate your results with, for example, results from Perth?
Say again?
How easy it is to correlate your results with those coming out of Perth?
What do you mean?
What I mean is that this is clearly a simulation, right? So
Yeah.
it's a coarser simulation than the actual
No. So the simulation is cycle accurate. So there's a whole CPU simulated. So you are basically executing the same code you're executing on your real system.
Right. So then, what you're saying that you don't get all the information because you don't know exactly how dependencies work.
Yeah.
So if you could correlate, you could
Ah.
measure this curve. Your results. Is there any way of saying it would not work?
Yeah, maybe. The main problem is that I guess it depends on your software. If your software executes very deterministic and doesn't depend on execution time of several subfunctions, that's possible. But like in this example, the execution of the whole system, because here we trace in this example a 64-core multi-core system, very differs because you have somehow different executions. The scheduler somehow does different decisions depending on this. So you have a very, very different execution of your software that looks very, very different, and therefore it's very, very hard to match against each other. Yes?
What's the slowdown running?
What?
What's the slowdown?
Oh, the slowdown is really tremendous, like in every simulation. So this strongly depends, obviously, on the number of cores, because the simulator is not parallelized. So if you run, for example, what we did at most, a 254 core simulation, this takes nearly forever. If you have a single core, you still have a slowdown. I guess at least, let me do the math. At least a factor of 10,000. So you cannot execute code that is really, really long. But that's also not the point, because here you mostly try to catch those functions that are very, very shortly, and you're not able to trace those other methods. Because if you have something running very long, the overhead and bias maybe not so much of an impact in comparison with you have something that runs very, very short. Yes?
I understand that this is very preliminary,
Yeah.
right? So you can just disregard this question. But how might this work when you have some closed hardware, like a proprietary GPU, for example, that's very hard to simulate?
This short answer, this will not work. Yeah, that's the problem. But like I said, it's better than nothing. So, for example, it depends what you want to look into. When you really want to look at the proprietary hardware, obviously you have no chance. If you just want to look at the host CPU part of your experiment, maybe you can reproduce the data of your proprietary device by previously recording it and just feeding it into the simulator. Actually, the simulator has, at least there was a paper, has a system C interface. So if you have the hardware description or can produce a hardware description that is close to the behavior of your proprietary hardware, you may be even lucky, but obviously this will not work out of the box, and probably you will put a lot of work into writing your simulator, so you have to weight how much effort you want to put where and how important this is for you.
Okay, let's thank Anselm again.